Hi everyone. As the title here indicates, this lesson is concerned with the basics of probability theory. We'll quickly review the notions of sets, together with set operations, namely union, intersection and complementation, and we'll then have a look at the basic building blocks for probabilistic modeling and define sample spaces, events and probability measures. Next, we'll briefly discuss how to compute probabilities on finite sample spaces, which essentially amounts to being able to count. Finally, we'll define the notions of conditional probability and independence. Let's start therefore by looking at sets and set operations. Intuitively, a set is just a collection of objects. We will leave this notion undefined. If A is a set and X is some object, then we say that X is an element of A or X belongs to A if X is amongst the objects that are collected in A. Note that the set is characterized entirely by its elements. In other words, two sets are the same if and only if they have the same elements. This can be a problem for the philosophers, for it implies, for example, that the set of all unicorns is equal to the set of all elves, because both sets are empty, in other words, they have the same elements. And indeed, one could argue that every elf is also a unicorn, because if there was some elf that was not a unicorn, then there would be some elf. But there are no elves. In mathematics, these problems never arise. We say that a set A is a subset of a set B if and only if every element of A also belongs to B. And we write A subset of B as follows. And A is a subset of B if and only if, whenever X belongs to A, then X belongs to B. In particular, two sets A and B are equal if and only if they are subsets of each other. In other words, if and only if A is a subset of B and B is a subset of A. We say that A is a proper subset of B if A is a subset of B but A is not equal to B. In other words, there are elements of B which do not belong to A. We also write B includes A to mean A is a subset of B. Be careful about the difference in meaning between the element relation and the subset relation. For example, the number 3 is an element of the set 135, but it is not a subset thereof. On the other hand, the set containing 3 is a subset of the set 135, but it is not an element thereof. Typically, there are just two ways to represent a set. On the one hand, you could list all of its elements. In other words, one could say A is equal to the set of all AI, where I ranges over some set. Or you can represent A by some defining property. Here A is the set of all x's which have the property phi x. I remind you that the following sets have special symbols associated with them. There is the empty set, which can be represented by listing all of its elements. It has no elements. Or by the defining property of being the set of all x which are not equal to themselves. The set n of natural numbers is the set that can be listed as follows: 1, 2, 3. Z plus is the set of non-negative integers, in other words, the same as the natural numbers, but also 0. The set Z of integers contains all positive and negative integers. The set Q of rationals is the set of all fractions P over Q, where P is an integer and Q is a natural number. The set R is the set of real numbers. And the set C is the set of complex numbers. Next, we will discuss the set operations of intersection, union, set difference, and complementation. Just some notation. We have here the Greek letter capital omega, and this will stand for the universal set, i.e. the set of all possible elements under consideration in the current context. In probability theory, this would be the set of all possible outcomes of a random experiment, for example. Then the letter that looks like a W is the Greek letter small omega and will stand for a generic element of the set capital omega. We show here some Venn diagrams of the set operations of intersection and union. Here the universal set capital omega is indicated by this rectangle, and the sets A and B, which are subsets of omega, are indicated by these circles over here. The intersection of A and B is denoted as follows and is the shaded part. By definition, the intersection of A and B is the set of all little omega belonging to capital Omega, which belong to both A and to B. In other words, intersection is AND. The union, on the other hand, of A and B is the set of all elements which belong to either A or B or both. A union B is the set of all little omega belonging to capital Omega, where omega belongs to either A or to B or to both. In other words, union is all. We also define the operation of set difference, A minus B. A minus B is the set of all elements which belong to A, but not to B, i.e. the shaded part here. Symbolically, A minus B is the set of all little omega belonging to capital Omega, where little omega belongs to A, but not to B. We also define the operation of complementation. A complement is the set of all omega belonging to capital Omega, where little omega does not belong to A. In other words, it's the same as the set difference capital Omega minus A. Everything which is in omega, but not in A. Now consider the following laws, some of which are self-evident and some which will be left as exercises. Firstly, we have the so-called idempotent laws. A union A is A intersection A is A. If you think about these are completely obvious. We also have commutative laws. A union B is equal to B union A. And similarly, A intersection B is equal to B intersection A. This also ought to be clear. In the same way, the associative laws, A union B union C is equal to A union B union C, and the same for intersection, ought to be clear as well. The distributive laws are a little bit more interesting and left as an exercise. A intersection B union C is equal to A intersection B union A intersection C. Notice here that A is being intersected with B union C, and that means that we must intersect A with B, and we must also intersect A with C. By interchanging the symbol of intersection and union, we obtain the other distributive law. Then we have the so-called absorption laws. A intersection A union B is A. Indeed, A union B contains A, and therefore if we intersect A with it, we get only A. Similarly, A union A intersection B is A, because A contains this intersection. Then we have the complementation laws. A intersection A complement is the empty set, because no element can belong to both A and A complement. And A union A complement is equal to omega, the universal set, because every element belongs to either A or to A complement. Of course, the complement of the complement is just the original. As an exercise, we also leave De Morgan's laws, which state that the complement of an intersection is the union of the complements, i.e. the complement of A intersection B is the union of A complement with B complement. The same holds if we interchange the union symbol with the intersection symbol. And finally, there are the set difference laws. A minus B union C is A minus B intersection A minus C. And similarly, A minus B intersection C is A minus B union A minus C.